In this video, we're going to practice a bunch of integration by parts. The formula for integration by parts is right here. We're going to assume that you've already seen this and maybe done a few problems. As we do these problems, we usually want to try to determine what u should be first. And as written here, you can see the general idea is that we choose u to be a function that becomes smaller, something that when you take the derivative, it gets to be a simpler function. And we're going to use the mnemonic ILATE. Sometimes it's written as L-I-A-T-E, but that's going to help us choose u appropriately. So we're always going to try, if we have an inverse, make that our u. If we have a logarithm, we'll make that our u, and then so on and so forth on down. Of course, with any of these, if tabular integration is going to make your work simpler, go for it. At this point, we'll work through all the problems. I'd recommend pausing the video, trying all the problems yourself first, see how you do, and then come back to the video and watch only those parts where you might have gotten into some trouble. Let's get started. Number one, we're integrating x times e to the 2x dx. So we're probably going to, again, following ILATE, I'm going to grab x, which is an algebraic function, as my u. So if I let u equal x, that means dv is going to be e to the 2x dx. du is dx. v is equal to e to the 2x, right? We're integrating. We're going to need a half here, right? So at this point, you can pause real quick and just go ahead and take a derivative of this. If you take a derivative of this, you're going to have 1/2 e to the 2x times 2 because of the chain rule, and it'll take you to the dv up here. So our integral x e to the 2x dx is equal to, we multiply across here, u times v, that's going to be 1/2 x e to the 2x minus the integral of v du. So we're going to get our 1/2 e to the 2x dx like that. And now we just need to integrate 1/2 e to the 2x dx. We have the 1/2 out here. The antiderivative of e to the 2x is going to be e to the 2x, but then we're also going to need another half here, and of course a plus c. So we end up with something that looks like this. We could have done this with the tabular method as well, and it probably would have been a little bit faster. Let's look at number 2. Again, we'll let u equal x, the algebraic function, and dv will be sine 4x dx. du equals dx, and v is equal to negative 1/4 cosine 4x. Again, you can take a derivative of that and see that it'll take you back to sine 4x. So our integral becomes, multiplying here, negative 1/4 x cosine 4x minus the integral here. Well, we have minus a negative 1/4, so that's going to become a positive 1/4 integral of cosine 4x dx. So now we integrate cosine 4x. And we end up with this. Again, number 2 would have been really good to do using the tabular method, but we'll move on for now. Number 3, integral of x squared cosine 3x dx. This time, I think I will do the tabular method on this, simply because this x squared is going to require us to do integration by parts more than once. So we'll just go ahead and write x squared followed by its derivatives all the way until it zeroes out. And then we have cosine 3x, and I need to integrate this all the way down until I get 4 iterations, right? Total of 4 iterations. So there's our first one. And then I think we're going to have a sine here, right? Sine 3x. But if I take the derivative of sine 3x, it doesn't give me cosine 3x. It gives me cosine 3x times 3. So I need a 1/3 here. And then again, another antiderivative. I think that's going to give us 1/9 cosine 3x. Go ahead and pause and take a derivative and make sure it takes you back to there. And then from there, we should get negative 1/27 sine 3x. And with this tabular method, we're going to end up multiplying here, multiplying here, multiplying here. And then because of the minus sign inside our formula, uv minus the integral of v du, that minus sign ends up flipping the signs. So the first one will be positive, the second one will be negative, and the third one will be positive. And so this allows us to write our antiderivative immediately. So we end up with the positive product of x squared times 1/3 sine of 3x. So we have 1/3 x squared sine 3x. And now the next one, we're going to multiply 2x times negative 1/9 cosine 3x, but we have that minus sign there. So that ends up giving us a positive. So we have plus 1/9. Actually, let's write plus 2/9 because we're multiplying times 2. And we have x cosine of 3x. And then the last multiplication, we're going to have the positive product 2 times the negative 1/27. That'll give us negative 2/27 sine of 3x plus c. It's a little sloppy there, but it's all there. Okay, let's go on to number 4. So for number 4, we think again back to I-late. And we notice we don't have any inverses, but we do have a logarithm. And although it might be tempting to make the inside u, we're going to have a problem with that square there, right? So sometimes you have to kind of guess with this stuff and see what happens. So I'm going to let u equal ln x squared, and I'm going to let dv equal dx and just see what happens. So when we take the derivative here, we're going to bring the 2 in front. We're going to leave the inside alone raised to the first power, which of course I'm not going to write that, times the derivative of the inner function is 1/x with a dx here. And here, v is equal to x when we take the antiderivative going like that. And so our integral of ln x squared dx, we're going to multiply diagonally this way first. So we're going to get x ln x squared minus the integral, and now we have to multiply across here. And what you'll notice, which is really nice, is this x and this 1/x cancel. And so we're just going to be taking the integral of 2 ln x dx like that. Now, at this point, you may have this integral, the integral of ln x, memorized. If you don't, it's a separate u substitution. You let u equal ln, actually, let's do it off to the side. If we just looked at the integral of ln x dx, we're going to let u equal ln x du is equal to 1/x dx. And then we're going to let dv equal dx, so v equals x. And so this integral becomes uv, which is x ln x, minus the integral of v du. Well, again, the x's cancel, and we just have a 1 dx. And integrating that's pretty straightforward, and we get something like this. So we'll just plug that in here and be done with it. Distributing the -2, of course. And that puts us there. Moving on to number 5. So if we think of I-late again, we have no inverses, no logs, no algebraic functions, we have a trig function and an exponential. So I'm going to go ahead and let our u equal the sine of 3 theta and dv equal to e to the 2 theta d theta, like that. That means du is equal to 3 cosine 3 theta d theta. And v is equal to, well, I know when I take the derivative of e to the 2 theta, I get e to the 2 theta, but chain rule, I'd have to multiply by a 2. So we need a 1/2 in front, like that. So our integral e to the 2 theta sine of 3 theta d theta is going to equal the product u times v. So that gives us 1/2 e to the 2 theta sine of 3 theta minus the integral. I have to multiply across here, right? So we have the 1/2 times the 3. So I'm going to put 3/2 in front, like this. And we have the e to the 2 theta. And we have a cosine 3 theta d theta. Now, if you look at this integral that we have, or this integrand, I should say, that we have here, and compare it to where we started, they're very similar, right? Except for one has a cosine versus a sine. So we're going to have to go through this again. But as I'm sure you can imagine, we're going to get, again, kind of a similar iteration of this. But when we integrate cosine, we're going to get some version of sine, right? With the 3 theta and all that business. And maybe at that point, we can combine it with what we have on the other side of the equal sign here. Here, let's keep going, and I'll show you what I mean. If we let u equal cosine 3 theta and dv equal e to the 2 theta d theta, here, when we take a derivative, we're going to get negative 3 sine 3 theta d theta. And over here, we're going to have the same thing that we had a moment ago, right? Like that. And so let's go ahead and rewrite all this. So I'm actually going to copy this again. You'll see why in a moment. But we've got e to the 2 theta sine 3 theta d theta equals 1/2 e to the 2 theta sine 3 theta minus 3/2, and then we're going to need to multiply all of that. I should say the 3/2 times whatever our integral is going to become, right? And so we're going to multiply diagonally here, which is going to give us 1/2 e to the 2 theta cosine of 3 theta minus the integral we get when we multiply here, the integrand, I should say, when we multiply there. So first off, notice that we're going to be multiplying this half and that -3, right? So we can rewrite that as a -3/2. Of course, negative, negative, we can make that positive. So let's make that positive. And then we have our hold on. We've got our integral, I should say, of e to the 2 theta sine of 3 theta d theta. Like that. Now, remember, we have this to distribute, which we're going to do next. But then we'll see, hopefully, something potentially nice that's going to happen. So let's go ahead and see what we get. So I'm going to recopy where we started, or I should say what we're trying to solve for. And here we have 1/2 e to the 2 theta sine of 3 theta. And I'm going to distribute this. I'm going to distribute this guy here and here. And we're going to get what? We're going to get minus 3/4 e to the 2 theta cosine 3 theta. And then that second multiplication, we're going to get a negative 9 over 4, the integral of e to the 2 theta sine 3 theta d theta. And now we're in a really good place, because if you look at this term here, this whole thing, it's an integral of e to the 2 theta sine 3 theta d theta. And that's like terms with this guy here. So we're actually going to add over the this purple term here over to the other side. Like this. Now, of course, this right here has a 4 over 4, right, a 1 in front of that integral. And so when we add these guys, we're going to get 13/4 integral of e to the 2 theta, I lost my d theta there, sine 3 theta d theta. Again, remember what we're trying to find here, right? We're trying to find that. So we're in pretty good shape here. Equals, we have our 1/2 e to the 2 theta sine of 3 theta minus 3/4 e to the 2 theta cosine of 3 theta. And all that's left to do is to multiply both sides by the reciprocal 4/3, right? In other words, we're going to multiply here by 4 over, I said 4/3, I meant to say 4 over 13, right? Multiply here by 4 over 13. And so we're left with the thing we're trying to find, this integral of e to the 2 theta sine 3 theta d theta is equal to, we're going to distribute that 4 over 13, right? We're going to multiply it here and multiply it here, and we'll get something like this. And of course, we have to finish it off with a plus c. So that one was pretty involved. We call that a wraparound integral, where we did this little bit here in blue, where we added the thing we're looking for to the other side to combine like terms and then solve for it. Let's go on to number 6. Number 6, the integral from 0 to 1 of t e to the negative t. We could do this directly, but this one we can also do with a tabular method, because if we let u equal t, when we take repeated derivatives, it eventually goes to 0. And if we take e to the negative t and we take the antiderivative of that, we get something like this over and over again, right? If I take the derivative of this guy, I get that. And if I take the derivative of that, I get that. So I think we should be in good shape. We're going to multiply diagonally like this, and the signs are going to start at plus, and then they're going to switch to minus. So we can go directly to writing this antiderivative. We're first going to multiply t times negative e to the negative t. And then we're going to multiply 1 times e to the negative t, but we need that minus sign. So we're actually going to be subtracting e to the negative t, evaluated from 0 to 1. And we evaluate at 1, we get negative e to the negative 1 minus e to the negative 1 minus, we're going to have 0 minus e to the 0. That gives us negative 2e to the negative 1 plus 1, or 1 minus 2 over e. Moving on to number 7. Again, if we think about I late, we start with inverse. Well, there are no inverses here, then we go to logarithm. So these are choices for u. So u is going to be ln x. dv, we're going to let be x to the negative 2 dx, right? I took the 1 over x squared fraction and wrote it as x to the negative 2. du will be 1 over x dx. V equals, we have to think, what do we have to take the derivative of to get x to the negative 2? Well, we need x to the negative 1 with a minus sign there, right? So again, pause for a moment, take the derivative. If you take this derivative, you get x to the negative 2. So we should be in pretty good shape. So we're integrating from 1 to 2, ln x over x squared dx, and that equals uv. So that's going to be negative 1 over x ln x minus the integral of v du. Well, I have a negative here and a negative here, so we'll just go ahead and make that a positive integral. This is the same as 1 over x. So when you take the v du, you're going to get 1 over x times 1 over x, which is 1 over x squared dx. And this is a definite integral, so we need to evaluate here from 1 to 2, and we still have to evaluate this integral from 1 to 2. With the first part plugging in 2, we get negative 1/2 ln 2 minus negative 1 over 1 ln of 1. Of course, ln of 1 is 0, so that's going to go away, but we'll do that in the next step. This guy right here is really x to the negative 2. So let's go ahead and rewrite it that way real quick. And then thinking about an antiderivative, well, we have x to the negative 1, and we're going to need a minus sign. So let's make this plus a minus sign. And then this is going to be evaluated 1 to 2. So we have negative 1/2 ln 2. This zeroes out. And then we have minus x to the negative 1 is 1 over x. So I have 1 over 2 minus 1 over 1. And of course, that will give us negative 1/2 here. So I think we get 1/2 minus 1/2 ln 2. Moving on to number 8. Again, thinking about I late, we're going to let u equal the ln of the square root of x. But wait a second. Isn't that the same as the integral from 1 to 4 of ln x to the 1/2 power, like that, dx? And isn't that the same as 1/2 in front, right, as a factor, and we just get ln x dx? I think that works. Now, we can take that half, leave it in front, and if we've memorized our work from earlier where we found the integral of ln x dx, and that's equal to x ln x minus x plus c. We're going to get x ln x minus x like that. And of course, we did this earlier using integration by parts, letting u be ln x and dv being dx. So you could do it all over again, but this one happens enough that it's worth memorizing. So equals 1/2. We have 4 ln 4 minus 4. And then we're going to subtract from that 1 ln 1, which is 0, minus 1, like that. So that's 1/2 4 ln 4 minus 4. Again, this zeroes out, and we have minus negative 1, which will be like adding 1. And of course, negative 4 plus 1 is a negative 3. So distributing, we're going to get a 2 ln 4 minus 3 over 2, which is a perfectly fine way to write it, but we can also notice that the ln of 4 is equal to the ln of 2 squared, and then that's going to be 2 ln 2. So we could also rewrite this as 4 ln 2 minus 3 over 2. Either way, gets you to the same place. Let's go on to number 9. Okay, again, thinking about I late. Immediately, we have an inverse function. So that's what we're going to let u be. So u is equal to the cosine inverse of x. That means that dv is equal to dx. Taking a derivative, du is going to be negative 1 over the square root of 1 minus x squared dx and here we have v is equal to x. So our integral from 0 to 1/2 cosine inverse x dx is going to equal, first we multiply here, u times v, that's going to be x cosine inverse x, and that's going to be evaluated from 0 to 1/2 minus the integral. Now we need v du, which will give us a negative x over the square root of 1 minus x squared dx. Of course, we have this negative business, which is no fun. Let's go ahead and make that just a positive like this. And of course, we still need our limits of integration. So at this point, what do we do with this integral? Well, we can do a u sub here, right? We can let u equal 1 minus x squared. Du is going to be negative 2x dx, making x dx equal to negative 1/2 du. We're going to have to change the limits of integration, and we'll get to that. But let's go ahead and take this bit and plug in the upper limit, 1/2, cosine inverse of 1/2, like that, minus 0 times whatever is 0. Now we're going to have to rewrite this here. Let's do it this way. Let's go ahead and take this guy and let's rewrite it in blue. So we're going to rewrite this in terms of u. First of all, you'll notice we've got this negative 1/2 du. So we have the plus minus 1/2 integral. We're going to get a du in back. And we're replacing x dx, right, which we've done that with negative 1/2 du. In the denominator, we have u to the 1/2 power, and then we have a 1 on top. Of course, we want to integrate, so I'm going to write that as u to the negative 1/2, like this. And we have to change the limits of integration. So if we put 0 in here, we're going to get 1 for the lower limit. And if we put 1/2 in there, right, plug 1/2 in there, we're going to get 1 minus 1/4 when we square half, and we'll have 3/4 up here. Moving on, we've got 1/2 cosine inverse of 1/2, and we'll come back to that in a moment. I'm going to change this to a plus sign and switch limits of integration, so we have the larger value on top, like this, u to the negative 1/2 du. So we have 1/2 cosine inverse of 1/2 is pi over 3. And then we have 1/2. We're adding 1 to our exponent there to get a 1/2 here, and I think we need a 2 to balance that out. As usual, take a derivative of this, make sure it takes you back to there. And we're plugging in 3/4 1. So now we have pi over 6 plus, we have u to the 1/2, right? The square root of u, because the 2's cancel, 3/4 and 1. So we have pi over 6 plus 1 when we plug in the 1 in for u, and then minus root 3 over 4 is the same as, let me rephrase that. The square root of 3/4 is the same as root 3 over 2. So we end up with pi over 6 minus root 3 over 2 plus 1, like that. You could make a common denominator, but let's just leave it there. Number 10, again, if we follow our mnemonic ILATE, we probably want to make u equal to ln of sine x, like that. That means dv is equal to cosine x dx. So du, the derivative of ln, is 1 over whatever's in there. So that's 1 over sine x, like that, times the derivative of the inner function is cosine x, and we have a dx here, and v equals sine x. And as usual, you can always pause and take a derivative and double check that you're getting that. So our integral cosine x ln sine x dx is equal to, we're going to multiply u times v. That gives us sine x ln of sine x minus the integral. Now we multiply across here, and you'll notice that the sine x's cancel. And so we just get cosine x dx. And we love that because we know that we can take that antiderivative quite easily. Antiderivative of cosine is sine, so we have minus sine x plus c. Number 11. Now, number 11 is kind of tricky. We clearly have an inner function. And when we think of an inner function, we often think of doing a u substitution. Let's go ahead and try that. I'm going to call it a w, though, instead of a u, for reasons to be seen in a moment. So if I let w equal the inner function ln x, that means that dw is equal to 1 over x dx. Now, that might feel like we're kind of stuck, but let's go ahead and rewrite this top equation in exponential form, meaning ln has a base of e, so we should be able to write e to the w equals x. And now if we take this equality here and multiply here by e to the w and here by x, it should still be equivalent. So this becomes e to the w dw equals dx. Let's see what this gives us. This is going to give us the integral of cosine of w, like that. But then dx in back is going to become an e to the w dw. And we didn't see this sort of u substitution in Calc 1 because it results in the integral of a product that we didn't have any techniques to deal with, but now we do. So continuing with integration by parts, we're going to let u equal, well, again, we can think about I late. And in this case, we don't have an inverse, we don't have a logarithm, we don't have algebraic, we have trigonometric, so we can let u equal cosine w. I think I did this problem earlier, letting u be e to the w, and that worked as well. And then we have dv is equal to e to the w dw. So real quick, the reason I chose to use w way back here instead of u was because I always like using u and dv when I'm doing integration by parts. So anyway, du here is going to be negative sine w dw, and v is e to the w. So we'll just go ahead and take the integral of e to the w cosine w dw, and we're going to multiply here. U times v is e to the w cosine w minus the integral, well, minus the product of these two, right? E to the w of negative sine e and negative sine w. So minus that negative will give us positive the integral of e to the w sine of w dw. And then we're going to do integration by parts again. So if we let u equal sine w this time, and dv is equal to e to the w dw again, here we have du is equal to cosine w dw, and here we have v equals e to the w. So we've got e to the w cosine w dw equals, we have our e to the w cosine w from our previous iteration of integration by parts, plus we're going to multiply here, so we have e to the w sine w minus the integral here which is going to be e to the w cosine w dw. And once again, you'll notice this quantity here, right? This term here is the same as this term here. So we're going to add that over, get two of them, and then divide by 2. So that's going to look like 2 integral e to the w cosine w dw equals e to the w cosine w plus e to the w sine w. Multiply both sides by 1/2. And we finally have gotten to this, but it's not quite the end yet, right? Yeah, I'm going to factor out an e to the w, so I get cosine w plus sine w. It's just a little less to write. Now, that's all well and good, but remember what we were trying to solve to begin with. We were trying to solve this thing, right? There were x's, not all these w's. So we're going to have to bring back ln x, right, over here, ln x for all of our w's. So let's go ahead and take a look what that becomes. So we have the integral of cosine ln x dx is equal to 1/2 e to the ln x. Well, what's e to the ln x? It's just plain x. So we'll just go ahead and write an x there. Cosine of ln x plus sine of ln x. And something I forgot back here is a plus c. So we have a plus c there. And so we end up with 1/2 x sine ln x plus cosine ln x in those parentheses plus c. Let's go on to number 12. So again, following ILATE, we can go ahead and let u equal the ln x that's being squared, and then dv is equal to x to the 4th dx. So here we have du is equal to 2 ln x raised to the first power times 1 over x, derivative of the inner function, dx. Here we're going to have v equals, integrating, we get 1/5 x to the 5th. Let's go ahead now and do this as an indefinite integral. It's just going to allow us to write a little bit less with keeping track of all the limits of integration, and then we'll bring it back at the end. So we've got uv, which is going to be 1/5 x to the 5th ln x squared minus the integral across here, which is going to be the integral of 2/5. Let's go ahead and put that in front. 2/5, the integral ln x. The x to the 5th and the 1 over x here and here are going to cancel to give us x to the 4th. So we're going to get x to the 4th ln x dx. Let's apply integration by parts again. U is equal to ln x. dv is x to the 4th dx. du is 1 over x dx. V is going to be 1/5 x to the 5th again. So now we're going to get 1/5 x to the 5th ln x squared minus 2/5 times uv is going to give us 1/5 x to the 5th ln x minus the integral across here, integral v du, which again, the 1 over x and x to the 5th is going to give us an x to the 4th dx like that. And now we're ready to do a quick integration here. 1/5 x to the 5th ln x squared minus, multiplying here, we're going to get 2 over 25 x to the 5th ln x. Multiplying here, we're going to get minus plus, right? A negative times negative. 2 over 25. Antiderivative, that's going to give us 1/5 x to the 5th, really plus c there. And we can go ahead and multiply these together. That'll give us a 2 over 125. So I'll go ahead and write that here. And now we're ready to take our original integral, which was a definite integral, and plug in the limits of integration into our antiderivative above. In other words, we're going to take this, we're going to plug in 2, and then we're going to plug in 1 and subtract. So we have 1/5, 2 to the 5th. When I plug in 2 right there, I'm going to get 32. So let's go ahead and write that as 32 over 5. Ln of 2 squared minus, plugging 2 in here, again, we get 32, but this time we're multiplying by 2, so we get 64 over 25 ln 2, plus, again, plugging in a 2 here, we get another 32 times 2 is 64 over 125. Subtracting from that what we get when we plug in 1. Well, when we plug in 1 right here into our x, that's going to give us a 0. ln of 1 is 0. The same thing happens right there. ln of 1 is 0. So we're just left with 2 over 125. And that will give us 32 over 5 ln 2 squared minus 64 over 25. I'll put this in parentheses, ln 2. And then finally, plus, subtracting, we get 62 over 125. Moving on to number 13. Again, notice we have an inner function here, so it's really tempting to start off with a substitution. So let's see what happens. If we let w equal x squared, then dw is equal to 2x dx. And a half dw is an x dx. So if we were to rewrite this integral as x squared e to the x squared x dx, all I did was take that x to the third and break it up into x squared times x, right? That's all I did, and kind of rearranged it in a weird way. But it's not all that weird, because now we have that x squared is w, so I get to write that, we to the w power, and then x dx, which is here, becomes a half a dw. So I'll put a half in front and a dw in back. And so now we notice we can do integration by parts here. If we let u equal w and dv equal e to the w dw, du is dw and v is e to the w. So this becomes 1/2. We're going to get uv, so w e to the w minus the integral of v du, which is e to the w dw. That's pretty straightforward integral. We now have 1/2 w e to the w minus e to the w, like this. We'll put a plus c in back. And of course, we have to bring back our x squareds. So we're going to have 1/2 x squared e to the x squared, distributing the half, 1/2 e to the x squared plus c. Moving on to 14. Again, we have an inner function, so we often want to try a substitution method. So if I let w equal x to the 1/2 power, then dw is equal to 1/2 x to the negative 1/2 power dx. So 2 dw is equal to x to the negative 1/2 power dx. But if you notice, we can use this again. We can multiply this side by w and this side by x to the 1/2. In other words, we can do this. 2 times that w dw is equal to x to the negative 1/2 times x to the 1/2 dx. And again, the stuff in blue is equivalent because of this up here. And so we're allowed to do that. And so we get 2w dw is equal to just plain dx. And so now we can rewrite this integral as 2w dw. That takes care of the dx. And of course, we have a sine of w like that. And now we can proceed with a relatively straightforward integration by parts. U equals w, dv is sine w dw, du equals dw, and v equals negative cosine w. And so we have 2 times uv, which is going to be negative w cosine w, minus the integral going this way, right? V du. Well, we have a negative cosine, and we're subtracting, so it becomes plus the integral cosine w dw. So now we're ready to integrate there, and we get something like this. And we'll go ahead and put plus c in back. So now we've got to bring back our x to the 1/2. So we have negative 2. Instead of w, I have x to the 1/2. I'll just go ahead and write root x, cosine of root x. And then again, distributing that 2 here, we get plus 2 sine root x plus c. Moving on to 15. Yet again, we have an inner function here. And so if we let w equal x squared, dw is equal to 2x dx. And again, just as we did above, I'm going to rewrite this as x squared cosine x squared times 2x dx. You don't necessarily need to write out that step, but I'm hoping it helps make clear what's going on. So this part here, this 2x dx, becomes a dw. And of course, our x squareds here and here are just going to be w. And so this integral becomes the integral of w cosine w dw. Let's go ahead and do a tabular method this time. If I take w and repeated derivatives, I get w1 and 0. If I take cosine of w and take repeated antiderivatives, I get sine w and negative cosine w. We will multiply here. We'll multiply here. This product has positive. That product will have a negative. And so we end up with w sine w, and then this minus and that minus give us plus a cosine w plus c. And so now we just have to bring back our x squared. So we have x squared sine x squared plus cosine x squared plus c. Moving on to number 16. Again, here we have an inner function. So let's go ahead and make that 4 minus x like that. dw is negative dx. So dx is equal to negative dw. And right about now, you might notice that you can also rewrite x as 4 minus w. So this integral, waiting on the limits of integration for a moment, we have 4 minus w replacing our x in front, right? And then we have the square root of just plain w, which we can write as w to the 1/2 power. And dx becomes a negative dw. Now, I still have to do the limits of integration, but the thing to notice here is we don't need to use integration by parts for this. We can just go ahead and distribute the w to the 1/2 power, let's just go ahead and do that real quick. I know I still need to do the limits of integration, but 4w to the 1/2 minus w to the 3/2 dw, we can now proceed, as we did in Calc 1, to just evaluate this. Let's go ahead and change the limits of integration. So we're going to plug in 0 here to get a 4 down below. We're going to plug in the 4 here to get a 0 above. And we can switch those limits of integration if we multiply by a negative. So I'm going to get rid of that negative and just put the 0 down here and the 4 up there. We can completely forget about the x's. We just need to evaluate this. So we add 1 to the exponent to get 3/2. And then we're going to need, I believe, an 8/3 in front. If you take that derivative, the 3's cancel, the 8 gets divided by 2, and you have the 4, minus, here we have w to the 5/2 with a 2/5 in front, and that's being evaluated from 0 to 4. So we have 8/3, 4 to the 3/2 minus 2/5, 4 to the 5/2, 4 to the 3/2. Well, the square root of 4 is 2, and then you're raising it to the 3rd power, which will give you 8. And 8 times 8 is 64/3. And then over here, we've got 4 to the 5/2. So it's the same idea. 4 under a square root is 2. 2 to the 5th power is 32. So that gives me a 64/5. Making a common denominator, I'll multiply here by 5. I'll multiply here by 3, and we'll have a 15 underneath. And when I have 5 64s minus 3 64s, I get 2 64s/15, also known as 128/15.